Diversity on calculus. Calculus is everywhere. The differentiation and integration of calculus have many real-world applications, from sports to engineering to astronomy and space travel. Calculus initially developed for better navigation system. Engineers use calculus for building skyscrapers and bridges. In robotics, calculus is used how robotic parts will work on given command. Electrical and computer engineers use calculus for system design. Calculus is used to improve safety of vehicles.
Calculus is a branch of mathematics that originated with scientific questions concerning rates of change. The easiest rates of change for most people to understand are those dealing with time. For example, a student watching their savings account dwindle over time as they pay for tuitions and other expenses is very concerned with rates of change, or the dollars per year being spent. Calculus kicks in when we get to circuits involving time circuits with capacitors or inductors. We have to use calculus to get a meaningful solution. Differential equations. When we solve first-order differential equations, we walk through the solutions step by step. As we move beyond resistor circuits and start to include capacitors and inductors, we need calculus to understand how they work. Think of calculus as a prerequisite in parallel with electrical engineering. You don't need to have a complete calculus background to get started, but it is helpful before too long.
In calculus, we have a special word to describe rates of change: derivative. One of the notations used to express a derivative or rate of change appears as a fraction. For example, if the variable s represents the amount of money in the student's savings account and t represents time, the rate of change of dollars over time would be written like this: ds over dt. The following set of figures puts actual numbers to this hypothetical scenario. Date: November 20. Saving account balanced $12,527.33. Rate of speeding ds over dt negative 5,749.01 per year. List some of the equations you have seen in your study of electronics containing derivatives, and explain how rate of change relates to the real-life phenomena described by those equations.
According to the Ohm's law, formula of a capacitor current is proportional to the time derivative of capacitor voltage, I equals C and dV over dt. Another way of saying this is to state that the capacitors differentiate voltage with respect to the time, and express this time derivative of voltage as a current. Suppose we had an oscilloscope capable of directly measuring current, or at least a current-to-voltage converter that we could attach to one of the probe inputs to allow direct measurement of current on one channel. With such an instrument setup, we could directly plot capacitor voltage and capacitor current together on the same display.
For each of the following voltage waveforms, channel B, plot the corresponding capacitor current waveform. Channel A, as it would appear on the oscilloscope screen.